Hello, it's noon time. We'll get started. Last 2 weeks, we work on the tokenization. And this 2 weeks, this week and the next week, we are working on the parsing tree. So basically, the tokenization, you actually break down the words into tokens. I mean, a sentence into the tokens. So let's see. For example, you have a sentence, I am home. Then actually, basically this one, you actually tokenize it to 3 tokens. And then basically these different tokens, they will get their so-called grammar analysis and then build a parsing tree. And then based on this parsing tree, translation will be done. So basically, this is what we say based on the grammar to build a parsing tree. So the kind of grammar we use to build our parsing tree is called context-free grammar. So basically, context-free grammar parser design, recursive descent parser design, token table-driven parsing design. So basically, this one we talk about the grammar and then how to based on the grammar to design the parser. And then the parser can also be designed in the ad hoc parser approach or table-driven parser approach. And there's a top-down parsing and also bottom-up parsing, 2 different type of the parsing can be used. So this parsing tree, basically you have lexical analyzer that actually generate the token streams. And then you actually, based on the token stream, you actually build a symbol table, and then you actually design a parser to analyze the token stream into the intermediate representation. And this one usually is parsing tree or abstract tree, syntax tree. Okay, abstract syntax tree. And then based on the abstract syntax tree, we may do code generation or translation. So parser is the heart of the typical compiler. So it's the most important piece in the software. And then it's a syntax-directed translation. And then here we have the input, and then you have regular grammar that actually translate the input into tokens. And you have context-free grammar to translate the tokens into your abstract syntax tree. And the abstract syntax tree with declaration, we call it semantic analysis, and then you create a semantic graph. And then based on semantic graph, you can generate the intermediate code and also the back end of the compiler. So parsing is to put token into parsing tree, and basically, for example, you have a times 2 plus 1, and in the a is an ID and is a operand. 2 is a integer, and then plus is an operator, and then 1 is an integer. So ID, then operator, and then integer, that will become a product expression. Okay, an expression plus a expression, you got a sum. Okay, so this is the so-called bottom-up parsing. So here you need to have the grammar. You also need to pop your data into stacks. So here you need to learn what is context-free grammar, the pushdown automata, the symbols, the non-symbols, the rules, the production rules, the derivation of the rules, the parsing tree, and syntactical form. First, we talk about syntactical form. Syntactical form is the starting symbol S of a grammar or any string that can be derived from S. So for example, you have SB, AB, S producing AS, S producing B, B producing B, BB, B is a state, and B can produce an empty string. So these are different Cs that you have. And then S is the starting symbol, B are intermediate states, and AB are basic symbols. So these are symbols, these are states, these are initial states, these are sentential form, the rules. And based on this, you can derive your S as AS or AB or ABB or ABBB or ABB. These are the assumptions that you can derive. So everything that can be derived by the rule and the grammar rule is called sentential form. Okay, that's a definition of sentential form. This one pretty important. Parsing, so analog of regular expression and deterministic finite automata. A context-free grammar is similar to that, but it actually can be more complicated because it's including the context-free language and it's an order of n square, n cube algorithm. And there's an indefinite number of the grammars for every context-free language. It turned out that for any CFG, we can create a parser that runs order of n cube time. There is two well-known parsing algorithms that permit this. Early algorithm, CYK algorithm, order n cube time is clearly unacceptable for a parser in a compiler, too slow. So parsing tool, okay, you have a parsing. So fortunately, there is a large class of grammars for which we can build parser that run in linear times. So linear time is actually a reduced format of the grammar, and you can call it LL or LR parsers that can run in linear time. But usually, as we say, the parsing is actually an order of n cube algorithm, but we want to make the compiler faster. So we try to limit some of the capabilities to find certain set of the grammar so that the compiler, the so-called parsing can be done in linear time or near linear times. And there are two classes of the parser, that's LR and LL parser. L parser means left to right, leftmost deviation. LR means left to right, rightmost deviation. These two different type of the parser. And LL is a top-down shape, top-down shape. And then LR is reverse, means bottom up. Okay, use this to remember the top down of bottom up. L is top down, R is reverse. So LL parser is also called top down or predictive parser. So you basically using predict tools to see if this rule apply. If that rule apply, we'll go deeper and go deeper and go deeper. That's called top down. Bottom up means that you actually, based on the basic elements, you write a matching rule, you build up rule to reduce the grammar, and then build up stage by stage. That's called bottom up grammar. So this kind of the grammar that actually can be linear type or near to linear type is called simple LR or LALR, look ahead LR parsers. These are special type of the process that can be done in more efficient way. So top-down and bottom-up parsing. So top-down parsing is that you basically check the rule. If it's okay, we detail to evaluate the right-hand side. If you find another rule, and you can actually keep expanding. So top-down is more like expanding. Bottom-up is more like reducing from the ID numbers and then back up to the rules. So these two approaches is totally different. Let's look at the LL parser. So when we actually try to parse a sentence, say right now, if we have A comma, B comma, C comma, okay, so you have something like this. So you will see this actually is a ID list, and you have an ID and ID list tail. And ID list tail can be further be explored as comma ID tail, and then this ID tail can further be explored as comma ID tail. Okay, something like this. So this is LL parsing. And then you can also do pattern up, starting with a single symbol on the left, and then see a comma. So see a comma, you do not determine it. You actually continue to see everything until your last element you see is finished. Then you know that this is common C ID tail. You move up as a ID tail, an ID tail with common ID and ID tail. You build it up as ID tail. An ID list tail with ID, you build up a so-called ID list. This is bottom-up parsing. Canonical derivation, at no point does the bottom-up parser predict what you will see. So bottom-up cannot predict. Bottom-up based on what you have. You read everything and then you process step by stage up. And so there's no rollback problem, but top-down you do have the rollback problems. So bottom-up, we also sometimes call it shift-reduce parsers. Because bottom-up parsers are the first to receive careful formal study, rightmost derivation also sometimes called canonical. So canonical, this term is for the bottom-up approach. So bounding space with bottom-up grammar. So basically, you build up your grammar basically with bounding space. Parsing. So you have a LL1 grammar. One means one bit look ahead, one word look ahead. Okay, so this actually LR1 is also has one look ahead. Okay, so not this number actually predicting how many characters you look ahead, or how many words you look ahead, how many tokens you look ahead. Okay. So parsing LR parsing with one token look ahead is called LR1 parser. So this is one family of the parser. So right here you have expression to be turn, or expression operator and turn. And your term can be vector or term multiply a vector. A vector can be a variable number or minus variable or an expression. And then your operator can add operator can be plus minus, multiply operator can be time or division. So this is one set of the grammar. So your type of parsing, you have bottom up and top down parsers. So here are different type of bottom up parser. Here are different type of the top down parsers. And pattern parser are prediction and backtrack type. But it doesn't need more memory to store. And this bottom up, you do need more memory to store. So first one, we talk about the top-down parser that's called recursive descent parsing. Recursive descent parsing means that you try to match one rule, and then you try to go deeper. If this rule doesn't apply, you go back, try another one. and try until there is a lure that can be applied. Okay, so this one is actually kind of like back first searching for the grandma tree, lure tree, similar to that. So recursive descent. Right here, we do have one example. So this example, you can watch the video that we provide, and then we'll figure out how this recursive descent can be done. Here, I don't actually explain it one more time. You actually need to watch the video. And basically, this one just show you a token by token evaluation of a simple pattern. In the middle, some lure may have backtracking or backup, but you will try to pass it the whole process of passing. This is called recursive descent scanner parser. Backtracking is that when you go into some function that fail, you don't actually match the lure, you do backtracking. Okay, and right here it show you how to build a recursive descent parser. So this one basically is a ad hoc parser design. So you can just build a lot of function to do it, or you can use a parsing table to do recursive descent parser design. So here show you the process of building a recursive descent. So basically, it is matching different rules. And if you matching the rule, you're going go down to deeper function code. So basically, recursive descent is based on the rule, and each rule is a function code. So the statement or expression, you recursive calling these different functions to evaluate your grammar two rules. Okay, that's actually top-down parsing, and then we may also have the bottom-up parsing. So bottom-up parsing is called LL. I'm sorry, but this LL parsing is top-down parsing. Top-down parsing actually is very easy or straightforward to implement. So here, this is a parse tree for the average programs. And you can also build a recursive descent parser with a tool. So this one, basically, you using the so-called Lexer to build a lexical analyzer, and then you can also build parser using the pre environment. Okay, next one is writing the LL1 grammar. So before you develop the compiler or the parser, you need to write your grammar. And LL grammar has a certain rule that you need to follow. Number one, you need to eliminate the left recursion, and then also you need to remove the left factorization. So the so-called left recursion is that if you have a term that you call your term by itself, this is called left recursion. So this left recursion rule cannot be used for LL parsers. So if you have an A rule, produce A rule plus alpha symbol, that actually is a left recursion. Your recursion happen on your first symbol, that's actually not allowed. So you actually need to modify your left recursion rule to the right recursion rules. And then they may also have the common prefix. Common prefix means that you may have this rule you can use or that rule you can use. So that also is no good. So we will actually do factorization to make the ID in front and then argument listed later, something like that. Okay. So we do adjustments. So we move the ID in front, and everything else is called statement. This the tails. This is the tail. Tail can be this one or this one. So you kind of like factorizing out the common factors. So these two are important things that you need to handle when you design the LL grammar. That is the elimination of left recursion and also left factorization. Okay, so that's the rule, and then also you need to remove the dangling else. Dangling else also need to be handled. So dangling else, you just make sure that your length stay with the closer if. That will remove the ambiguity. Sometimes some language do have the if then and else end. Okay, something like that is structure, but it actually is not efficient. So it was changed to if then else if else if else if else and else and end. This type of the new program. So this actually is used in Python. Okay. Next one is the table-driven design for the top-down parser. So here we show you how to design a top-down parser, table-driven top-down parser. So it actually use a table of the next state, okay, and the next possible rule and the next possible input tokens, and use that to pass your programs. Okay, and here is the result for passing. Okay, and then there is a build and predict set. You need to study for the build set and predict set. These are very important, so you need to watch the video carefully about how to generate first step, follow set, and predict set. So first set means that what is the duo's first symbols? That's called first set. What follow set means what's the set of the symbols that actually follow my current rules. Predict set means that what is the symbol that can be predicted as the next symbol from my current rules. So these three sets are very important. Okay. So your first alpha is the all of the rule that actually you will produce. The first symbol that you will produce, we call it the first set. Follow set means that you have a certain rule, and then it will be followed by what symbols. Then after this current rule, what is the next symbol you may see? That's called follow set. And then predict set means that is what you will predict from the current you will see from current rules. Okay, so you need to go and study how this different set being built. So here is an example, and it show you how to build up uh, the whole predict set first step. So it actually will go back to use the rule one by one to build this the table. So the detail I also don't show you right here. You need to watch the video. Okay, so here show you how to complete first set, follow set, and the predict set of different rules. Okay, that's the LL parsing part, and then the second half of the class of this lecture is the LR parsing. LR parsing is using different parsing rule, but normally the typical compiler you will see are mostly LR parser now, not LL parser, because LL parser your grammar is more limited. So here show you the family LL0, LL1, LLK, okay, and then these are different LR family and show you the relationship of these different grammars expression power. Even the bigger set means that the language is more powerful, but the compiler will be more complicated as well. So there is a trade-off between your expression power of your grammar and also your compiler efficiency. So with some limitation, you may design a compiler that with robust performance and enough expression power. That would be the goal to design a good compiler. So here we have the model of a LR parsers using the action and go to build a table-driven LR parsers. So here you do have a grammar rules and then the pre-compiled table. And using that, you to generate your parsing activities. So again, this table, we don't go through it one more time right here, okay? You need to watch the video in this chapter. It's very tedious, so I don't repeat it one more time. And then it go down to the example of how to use it. Okay, here has a detailed tracing of some cases. And then here is configuration state characteristics finance state machine. Okay, or a certain parser. And then it's the transition table. And then the parser design. Okay, so there are different variants for the LR parsers. And again, there is a trade-off between the expression power and the compilation speed. You need to pick the right one for yourself. Typically, if you compile your grammar is can be more detailed expression, then the efficiency will not be as good. But if you want to have a good efficiency, then your grammar may need to be limited. So there is a certain trade-off you need to make. So usually the compiler is using LSR, SLR or LALR parser. Usually these are the typical more popular one, commercial use. Okay, there are certain rules. We don't go into the details. So this chapter basically teach you how this LR and LL parsers been built. And we don't go into the detail again in here. We basically, this Monday session is set up for the review of the problems and also help you to study. Sorry, I don't see anyone showing up. So I'm going to stop right here for this week, and hopefully if you have questions, let me know, okay? See you next time, bye-bye.